Welcome, everybody, to this week's CDAR Risk Seminar. We appreciate your accommodating our last-minute change from in-person to online, and great to see everybody. It's my extreme pleasure to introduce, I'm Lisa Goldberg, CDAR's co-director. I guess you all know me. And it's my extreme pleasure to introduce this week's speaker, Lynne Burks, a seismic data scientist who will be telling us about resilience analytics to measure physical risk at scale. So turn it over to you, Lynne.
All right. Thank you, Lisa. And thank you, everyone, for inviting me. I'm very sorry that I couldn't be there in person today, but I'm glad that I still have the opportunity to share what we're working on at One Concern with all of you. Yeah, as Lisa mentioned, my name is Lynne Burks. I'm a seismic data scientist at One Concern. So One Concern is a resilience technology company based in Menlo Park, and I'm going to share a little bit of what we've been working on. So with that, we'll just kind of jump into the presentation. So here's an outline of what I'll talk about today. So first, I'll give you kind of an introduction and overview of One Concern's resilience analytics platform, which is kind of the main product and all of the models that we're working on. And then we'll kind of talk about two of the main components of the platform. The first one is the digital twin. So I'll give you an overview of what a digital twin is and what One Concerns contains. And then we'll do a little bit of a deep dive into one portion of the digital twin, which is the power distribution network and how we generate that data. And then the other component of the resilience analytics platform that we'll talk about is the resilience prediction. So we'll kind of talk in detail about one of our models, which is the seismic machine learning model that we use to predict damage to buildings from earthquakes. And then we'll also talk a little bit about kind of the final outcome of the platform, which is the resilience score. And as I'm going through this presentation today, feel free to interrupt with questions at any time. If you would like to ask something, we can definitely make this more of a discussion. And then hopefully we'll also have some time left over at the end for any remaining questions that you guys have. So I'll start out with just a quote, kind of a famous quote from Galileo. He said, "Measure what can be measured and make measurable what cannot be." So this is a quote that we like at One Concern because we think about resilience, which is kind of an intangible thing that a lot of people are really interested in understanding right now. And kind of the first step in being able to understand and then eventually mitigate your resilience is making it measurable. So that's really the main goal of what we're trying to do, and what our analytics platform is really set out for, is thinking about how can we measure resilience, and then maybe once we can measure it, we can better understand what's contributing to it, and then we can help to solve it and maybe mitigate some of the risks that show up through that process. So here's an overview of the One Concern resilience platform and sort of the main components that go into it. So the four main things, the first one is what we call the digital twin. This is basically a really large data set that contains kind of details about the built environment. So we've collected data about all of the buildings and infrastructure that you might be interested in understanding in order to understand the resilience of a community. So we've collected and curated data about buildings, different types of infrastructure like the power network, transportation networks, including bridges and highways. And we've basically built that data set, filled in all of the gaps, and turned it into a cleaned data set that we can use. The next big component of a resilience platform that we've included is natural hazards. And so we consider earthquakes, flood, and windstorm in our resilience platform. And we also consider the impacts of climate change on flood and wind. And so these are the hazards that we currently model, and we can basically model how those will impact our digital twin. And the way that we do that is kind of the third component of the platform, which is shown here as the impact and recovery. And so this is basically a set of subcomponent models that model the damage, which would be the impact, and then also the recovery time. So how long it takes those systems to recover after they've been damaged by one of these natural hazards. And so we have component models for a lot of the things shown on this slide for buildings, power, airports, and roads, and other pieces of infrastructure. And those models that model the damage and downtime to each of those components are a lot of the kind of model development that we've done at One Concern. And then the final kind of component is the resilience quantification. So once we have a sense of the damage and downtime to all of these different components, how do we combine it into kind of a final resilience score or a way to quantify the resilience that can sort of be quickly and easily used? So here's a little bit more details about each of those steps in the resilience platform, along with some numbers for our US platform. So on the left, a little bit about the digital twin and kind of what we've created and curated there. So you can see all of the different main components that are in the digital twin. Contains commercial buildings and residential buildings. In the US, we have about 39 million commercial buildings and 108 million residential buildings. So as you can imagine, this is a really large data set. And one of the things that we've done is kind of taken these buildings from different data sets and curated it and filled in any of the gaps and put it into kind of a central location, making it easier to use. The digital twin also contains a lot of information about different types of infrastructure in the US. So we have information about 25 seaports, 128 airports, 2.7 million highway segments, and 600,000 bridges. And then there's also information about the power networks, so 45,000 power substations, and then a whole bunch of power lines and power poles. And then a few more details about each of the hazards that we model. We model earthquake, flood, and wind. And for flood and wind, we do consider climate change. So we model kind of a baseline climate for both of those hazards, as well as considering some RCP scenarios, 4.5 and 8.5. And we have different views into the future. So we have kind of the current year of 2020, and then we also consider the impacts of climate change in 2035 and 2050. And then the main outcomes of the resilience simulation are shown on the right of the slide. So the main things that we predict are the damage ratio to different buildings. So this is a direct measure of damage to the building itself. And then we also predict downtime and full recovery curves for each of the different types of assets in the digital twin. So we have models to predict like the downtime to airports caused by earthquake or the downtime to bridges caused by earthquakes. And then the recovery curve is basically the full probabilistic distribution of that downtime. And that's the main outcome of our models.
Can I ask a question? So looking at the first two bullet points, the first, I think, is covered by standard insurers, right? That's traditionally how much of the building is damaged. It's the kind of the second thing, the business loss, that's newer.
Yep, that's exactly right. So yeah, traditional insurance policies really hinge on the building itself. And that's what a lot of traditional catastrophe models also focus on, right? So there are a lot of catastrophe models in industry that insurance companies use, but they're really focused on modeling that damage to the building itself. And then typically what they do to model business interruption or the downtime from that damage is they just kind of take the loss to the building, and then they assume that some percentage of that building damage loss is equal to the business interruption. So they're not really modeling the downtime explicitly. So that's where a lot of the kind of new information comes in from one concern.
And maybe you'll explain this a bit later, but are your estimates of damage to buildings consonant with traditional insurers or different in some way?
So it kind of depends on which building and hazard we're looking at. So for example, I'll get into a little bit more details about our seismic machine learning model, which predicts damage to buildings. So that's one area where we've done kind of our own research and developed our own model. And then we have compared our results to kind of traditional CAT modeling results and, found consistency there. But then for some other, like for flood and wind, actually, we just use vendor models to predict damage to buildings. So for that component of our resilience platform, it would be kind of the same as what you get from a traditional catastrophe model.
Great.
And the new part that we bring in would be the downtime from those hazards.
Got it.
All right. Yeah, good question. Thanks. Okay. And so kind of as an overview of some of the use cases for these resilience statistics, this slide is showing on the left kind of some visualizations of things that you can do with the outcome of our platform. So one thing is, right, discovering vulnerabilities. So what's shown here is kind of, if you have maybe a set of buildings across the US, you could look at the resilience statistics for all of them and maybe identify the buildings that are the most vulnerable from a downtime perspective, and then maybe do more of a deeper dive on those. And so then you could dig into what we call here the downtime insights. So looking at the downtime to that building from each of the lifelines around it, and trying to understand maybe what is the biggest contributor. Another thing you can look at is the first to fail. So this is kind of related to the different lifelines. You can look at a specific hazard level. So like looking at a 100-year return period flood and understanding which of the different infrastructures around your building might be the first to fail in that kind of scenario. So that can help you maybe prioritize which lifelines you would look at for mitigation, or which buildings you might look at. You can also do national benchmarking. So we have calculated these resilience statistics for all of the buildings in our digital twin. So you can pretty quickly look at maybe buildings that you're interested in and compare it across any other buildings that would be in our digital twin. So all of these use cases can kind of be used to help with the things shown in the bullets on the right of the slide. So you can use this information maybe as a business to inform your continuity planning or inform your mitigation planning. You can also, optimize your resource allocation. So maybe if you need to choose between a few different buildings to invest in, you could use this to choose which buildings you would want to, maybe mitigate and help reduce the downtime for those buildings. You can quantify the impact of disasters, including climate change. And this quantification could maybe even help you do something like a resilience transfer. So maybe buying more insurance to cover different buildings where you have maybe more of an issue or more impact. So these are some of the things that we've thought of for resilience use cases, and that some of our clients are interested in using this data for. So one other thing that I want to highlight about the One Concern Resilience Analytics platform is kind of the size of the data set. So here's just kind of a schematic showing a comparison between more conventional catastrophe models that Lisa mentioned. These models typically concern buildings only, as she mentioned, and maybe use hundreds of kind of static data points. And they're really interested in kind of damage to building components, and then from there, estimating the downtime is just kind of a percentage of the damage to the building itself. This is in contrast to the One Concern framework, which looks at trillions of connected data points. So we're looking at infrastructure systems, which we kind of think of as layers. And so we're basically looking at networks and systems, many different data points, looking all around the commercial building of interest. And here's just kind of showing the different layers that we have considered, including commercial and residential buildings, transportation networks, which includes bridges, highways, airports, and ports, and then power systems, so including substations and power poles and lines. So now I'll get into a little bit more details about our digital twin. So first, a little bit of background about kind of what is a digital twin. Basically, it's kind of a fancy name for something that's just a virtual representation of built objects. So it's just a large data set where we've basically curated and collected data from a bunch of different sources and brought it all into one place. It also provides us a virtual environment to kind of simulate physical processes. And what that means is we can basically take our different hazards and apply them to the entire digital twin. So as I've mentioned, we've done that in the US for the hazards that we model. So we've sort of pre-calculated the downtimes from all of the different hazards across all of these buildings. And so we've used this as basically a simulation process to understand the downtime across different hazards and different lifelines and buildings. So it's really just kind of a granular and detailed map of our world. And, it really enables us to do kind of a comprehensive resilience analysis where you can compare one building to another. So this slide, again, is just kind of highlighting in terms of the numbers of the different types of infrastructure that we have in the digital twin for the United States. So we're really focused on transportation, right? Ports, airports, bridges, and highways. and then the power system, so substations, and power poles and lines, and then buildings. And really, I think one of the main values that you get from this digital twin is that you can imagine all of this data came from many different sources. So some of it might be available publicly, like from government sources. Some might be coming from a vendor, but it would be in kind of a different format than the data that would be available publicly. And also you can imagine a lot of this data, even if you can get it from a public place or you can buy it from a vendor, might not have all of the features that you need in order to do a resilience analysis, or it might be missing some features for some buildings. So what we've done is really take this data from all of these different sources and filled in those gaps to make sure that we have a complete data set that we can use as input to our damage and recovery models. So as I mentioned kind of briefly, some of the challenges associated with the digital twin is the data accessibility. Some of the data might be available publicly, but some not. So we have purchased data from vendors. We've also gone out and scraped data from many different sources ourselves. Some of it, might only be available privately, and we can get access to it through some kind of partnership. Another challenge is data scarcity. So a lot of this data just isn't even available. And one of the examples of that I'll get into some more details on is a power distribution network. A lot of times that information just isn't even available, or it's owned by a utility company and they're not willing to share it, or they might have lots of holes in their data, even if they are willing. Also the scalability, right? This is a really large data set. So that can be a challenge when you're working with lots of large data. And then gaining trust. So, making sure that we understand truly what all of the features are, and that when we're doing imputation or bringing it from different places, that we're filling in that data in a valid way. And so some of the solutions that we've used here include machine learning and data science in order to fill in those gaps, using parallel processing and high performance computing, and then doing validation as much as we can when we can with ground truth data where it's available.
Do you use simulated data as well?
Yes, we do. And so I will share an example of where we use it specifically for the power distribution network. That's where we actually there's really no data available or very limited data. And so we use a simulated power network. And then we will also simulate if there's any holes in the data, like important features for buildings. Like for example, a lot of the buildings data that's available in the US would be coming from something like a tax assessor's office, right? They might collect information about buildings across the whole US, but there are certain features that a tax assessor might not really care about, like the structural system, but that's something that's really important in order to understand the performance of that building in a natural hazard. So we need to kind of fill in those gaps where it's not available. So that's another place where we use simulation. Yep. So now I'll get into some of the details on where we do that simulation on the synthetic power distribution network. So first, just a little bit of background about the power grid itself. So this kind of a simple figure is showing all of the main components of the power system in the US. So power starts out at a generating station. So this would be somewhere like a wind farm or a solar farm or a coal burning power plant. And that's where the power is generated. And then it's transmitted along transmission power lines across long distances to a transmission substation or through a transmission substation. And so these are, kind of like the really big tower power lines that you might see in rural areas or coming into a city, and they would cross a really large, long area or a long distance. And then that power is brought to a distribution substation, and this would be a smaller substation that would reduce the voltage of the power before distributing it out to the final customers. So the distribution substation would take in the power from transmission lines and then put it onto distribution lines, which would then put it out to the users, which would be buildings. So homes or commercial buildings like office buildings and retail buildings that are actually using that power. And so the power network that One Concern currently models in our system is just the distribution network. And so that's the part that's highlighted in green on this slide. So basically the distribution substation, and then the power lines and poles that carry the power from that distribution substation to the building. And so this is kind of the last step in the overall power grid. And this is the part that we are modeling. And this is a part that is pretty commonly damaged, especially in natural disasters. Like you think about hurricanes, a lot of damage happens to the power lines and power poles that carries the power kind of to the final customer. And then, unfortunately, this is also the part of the power grid where we sort of have the least amount of publicly available data. Generating stations and transmission lines and substations are generally kind of controlled by the federal government. And so you can get some information about them from the federal government, but distribution systems are really controlled by individual utilities, and they are typically not willing to share that information, or they might not even have very detailed information themselves about the location of all of their power poles and lines. So what we need to do is actually generate a synthetic network and then use that in order to model the damage and recovery to it, to model potential power outages.
And I wonder if you've talked at all to PG&E, because like their distribution systems go down constantly. And I think that they'd be very pleased to talk to researchers who might help them better understand what the issues are and how to address them. They certainly claim they're interested in that in their commercials, but have you had direct experience with them?
We do. We have had some conversations with PG&E, and one of the, I think, interesting things that they, wanted to know from our research, and this actually gets into, I think, like the level of data that they even have about their system, is they know, and they model their system kind of down to a distribution circuit. And so that would basically be like one substation and then kind of the buildings that are connected to it. But they actually don't know or have that much information about at an individual building level, whether the power is on or not. They modeled just down to a distribution circuit. And that's how they think about it, is kind of like from that level of resolution. And so being able to actually go down to an individual building level is something that they are kind of interested in. And I think maybe a little bit from a PR perspective, because that would enable them to talk about what's the impact to our customers specifically, like looking at individual buildings and whether or not they have power. And that's something that I think they don't have a great handle on right now. And so we have had a few conversations with them about it. We don't really have any current ongoing projects with them, but we've had some interesting discussions. And so maybe we'll see where that could go.
What you say really surprises me, because I have an app or no, and they will tell me, like, there's always power going down in the Bay Area, and they will tell me that the power is off at my house. You put in your address. So maybe that's not true. Maybe they're just telling me the power is off in some group of houses. I mean, maybe they don't know. Are they just, what are they saying when they tell me that?
So I think they are modeling down there to like the distribution circuit. So they know that it's like your house is connected to a circuit with some other houses, and they know that that circuit is out. And so then they can alert all of the houses in that circuit. But if there was something even more granular happening, like your house and not your neighbor, if you were on the same circuit, they probably wouldn't have that level of understanding.
Okay, I'm going to watch for that.
Lynne,
Things happen.
I have like Lisa beat me to that question. Like we're all affected by PG&E power outages, but I was wondering if you ever talked to state of California, because it seems like the state would be very interested in having this data, like and just like for pure economic impact, to know like which buildings get affected and which businesses go out. Did you ever have contact with that?
I don't know if we've talked specifically to the state of California. I know we've had conversations with like California Earthquake Authority, and they're in charge of, like insurance for residential buildings to earthquakes. And they're definitely interested in our models and data. I mean, if we had some connections with the state of California, we would definitely be interested in talking to them and understanding how they might be able to use the information. But I don't know if we've had any kind of specific conversations with them.
It seems like would be pretty relevant data and models. Thank you.
Yes, thank you. Okay, so yeah, and thanks for all the questions. This is a great discussion. So now I'll get into a little bit more about how we generate that power distribution network. So this speaks to kind of the digital twin creation. So the main inputs to our power distribution network model are shown here on the left. So the main inputs are the distribution substations and their locations. The locations of the buildings, which are like the consumers or the end customers of the power, and then also the road network, because typically distribution lines run along roads. So that helps us kind of predict where the distribution lines are likely to be. Substations is highlighted in orange on this slide because it is one place where we do use machine learning to help kind of augment that data set. And I'll show you a little more details about that on the next slide. And then given all of those inputs, the way that we generate the synthetic power distribution network is first we start by basically assigning each customer to a substation. So we look at the closest substation around each building, and there's some probability that each building is connected to a few closest substations. And then we also generate the power components. These would be the power poles and the power lines. So we generate the locations of those. And then we also have a model highlighted in orange here, which is the network system type identification. What that means is we basically need to identify for the power lines and poles, the main type of them, which means is it overhead or underground, because that will have a big impact on the resilience of the system, whether the power line is running above the street or if it's in a tunnel underground. And so we have a machine learning model to predict or to classify the distribution network that way. And then given those two components, then we kind of optimize the network to make sure that each building is connected to a substation, and that's where it's getting power from, and then what the system basically looks like in between that substation and the final customer. And then the final outputs of the digital twin are all of the network components, so the location of the power lines and poles and their attributes, and then also the topology of the network. And then this network system is what's input to our damage and recovery model to predict, if a hurricane or an earthquake happens, which components might go down and how long will it take to repair them. So here's just kind of a high-level summary of the power substation information that we use in the US. So there is some public data available, at least in the United States, for distribution substations. And this comes from the federal government, from the Homeland Infrastructure Foundation level data. In the US, they have about 50,000 substations. But from other sources, like the Department of Energy, we expect to have over 70,000 substations in the US. So this is about a 30% gap that we have in the data that we need to be able to fill in a scalable manner. And also speaking to that, we would like to have a model to identify substations that we can use outside of the US, because the United States has really nice publicly available data. But if we want to model another country, it's unlikely that they'll have such nice clean data as the US government has. So we also want this approach to be kind of scalable in case we move, or for when we move outside of the United States. So what we did here is we used a computer vision model. We basically used satellite imagery and deep learning because substations are identifiable from satellite imagery. They have a pretty consistent way that they look from the air. And so you can kind of scan over satellite imagery and be able to identify the locations of substations. And so this is something that we have been working on. It's kind of a research project that we're doing in the US, and we've been able to identify substations this way. And then another place that we use machine learning is in the distribution system. As I kind of briefly mentioned before, there are two main types of components in a power distribution system. One is an overhead system, and that's what's shown in the picture on the top of the slide here. So this is sort of the typical wooden power poles that you would see, everywhere in maybe like a residential area or a smaller city. So overhead systems are very common because they are a lot cheaper to build than underground systems. And they do have a relatively shorter repair time because they're a little bit easier to access than underground systems, but they're very vulnerable to wind, earthquake, and wildfire. So it's important to understand whether you're dealing with overhead or underground system, because an overhead system is much more likely to be damaged in something like a hurricane or an earthquake or in a wildfire. And that's in contrast to an underground system, which is shown on the bottom right. These are basically tunnels underground where the distribution lines are running. These are very expensive to build, and it takes longer to repair them because it's more difficult to access them if they are damaged after an event. But even though it takes longer to repair them, they're much more resilient to both wind and earthquake. So they're much less likely to be damaged, but they are vulnerable to flood. So it's really important to understand in the system which type you're dealing with. And so we have a model that's a two-stage process, and we do that in order to support scalability of the model, to identify and to predict whether any component is overhead or underground. So as you can imagine, you can use a computer vision model to model this because you can look at something like a Google Street View image and you can identify whether a power pole exists in that image or not. And if a power pole is there, then you would know that it's overhead. And if it's not, then you would know it's underground. But as you can imagine, this method is very expensive. You need a lot of data. You need Google Street images or some other way of getting lots of images of the area that you're trying to model. And it's very computationally expensive. So you can use this model in, maybe urban areas or areas with high importance that you really want to model correctly. It's also more generalizable. And it does have, at least in our models, a higher accuracy. You can see kind of a snapshot of the outcome on the upper right. The accuracy for this model is about 93%. But as I mentioned, it's difficult to deploy this model everywhere. So for scalability, we also use kind of a more simple statistical learning model. And we've tested out a few different ones. We use a random forest model, and you can use this in maybe more residential or rural areas. It's much more scalable, but it's not as generalizable because you need to have training data from that area. And the accuracy is also a little bit lower at 83%. And you can see just kind of a snapshot here of the important features that go into the random forest model. And these are features about the building that the power line is connecting into. So kind of the most important feature shown here is actually the year built of the building, because older buildings will tend to have overhead power lines and newer buildings might tend to have underground. But some other features like the square footage and the value of the building are important for predicting the type as well.
Lynn, is it your view that the underground is better? That if I were building today and you were to make a recommendation to me, which would you pick?
Underground, at least from the perspective of resilience to natural hazards. It's much less likely to cause power outages, but and also it's a kind of hot topic in California right now because you're much less likely to start wildfires if you have underground power lines. So I think there is a lot of pressure right now for PG&E to underground their lines because you're less likely to kind of get sparks that would cause wildfires, but it's very expensive and takes a long time to do. So that's the challenge.
True, but
So,
you also
go ahead, Lisa.
that you also mentioned floods, which I mean, it's always and difficulty of repair. I've watched this debate, and then at the end of it, everyone says that I've heard says what you just said, but I'm wondering if the other risks are being downplayed because the ones that are very much in our face are the wildfires right now. But that wasn't always the case, and we do have a lot of flooding here in California too.
Mm-hmm. Yeah, that is true. I think the vulnerability to flooding, right, it is there for undergrounding, but in an overhead, wind and earthquake, it's much more vulnerable. And I think the risk of starting a wildfire is now becoming, much more prevalent. And yeah, I think that might, kind of be more important than having power outages due to underground flooding.
Yeah.
So, but it is interesting because we've seen examples in our model. What we're ultimately modeling is the amount of time that a building will be without power following one of these disasters. And you do see, if you're looking at underground power lines, the downtime might be a little bit smaller, but it's not a huge difference. And sometimes that is counterintuitive for people at first, but it's because of this reason that it takes longer to repair when it does go down. So it's less likely to go down, but if it does, it takes longer to repair it. But yeah, so it's definitely a trade-off, and it can surprise people when they first see that result.
I saw Severin Bornstein. He's the campus guru for electricity generation, economic issues on campus, to the effect that PG&E wants to underground because it's involves a large capital expenditure, and then they can build it into their rate base and earn their regulated rate of return on that, and that actually exceeds the cost of capital. So he was skeptical about whether, in fact, this is wise public policy. I don't know any details of the analysis it's based on, but there's controversy, I think on multiple fronts on that. Obviously, PG&E would like to avoid responsibility for future wildfires if it can do so and get the costs covered by ratepayers. So, I was curious about undergrounding and earthquakes, because an earthquake can result in liquefaction, a variety of other things, which would seem to me likely to disrupt underground power lines. But is that not the case, that liquefaction isn't a problem, or is not as big a problem as having power poles fall over in the earthquake or buildings collapse onto them?
Yes, that's a very good point. Yeah, you definitely noticed that in the previous slide. And you're right, liquefaction would cause problems for undergrounding. So there are other maybe things associated with earthquakes that cause vulnerabilities for undergrounding, like liquefaction or large permanent displacements of the ground that might, cause issues in the underground tunneling. But I think overall, that's probably less frequent than an overhead power pole being impacted by ground shaking. And so, I think I guess we haven't explicitly studied that or done a trade-off analysis, but my, I guess, like intuition would be that it would be less of an overall impact, but it would be a new kind of possible failure mode that you'd be introducing by undergrounding a power line. That is true.
I had a question about ongoing research and development to bring down the cost of underground or low above ground. I don't understand the electrical engineering, but there is something wonderful about air as an insulator and otherwise that isn't shared by the ground, which is a ground as so what is the state of development on that? The model, I think, for undergrounding is still based on a much earlier paradigm where earth-moving vehicles come and dig a huge trench, and a great big cable is expensively constructed and buried. Are there new methods being considered, and how would that affect resilience?
That is a very good question, and I'll be honest, I don't really know. I'm definitely not an expert in the power network or undergrounding. I guess we mostly study it just from how, like, whether it's overhead or underground will impact the resilience. So in terms of like the methods that are used to underground, I'm not really that familiar with them or their trade-offs. It's mostly just from the perspective of, if it's underground, it's less likely to be impacted by wind, or there could be other things happening. So I'm really not sure of the latest research with that, but that's a very good question.
So the resilience analysis then would be based on classical models of overhead or underground, but it would be interesting to be able to see how improved methods could affect resilience, and at what point the newer methods could be cost justified. Thank you very much.
Yeah, that's a great point, and something that we haven't really looked at to see if newer methods of undergrounding, what impacts those would have on the resilience of the system. Yeah, thanks for bringing that up. Okay. All right. So yeah, next I'll get into kind of the other main component of the platform, which is the resilience prediction. So this is the part of the platform where we predict damage and downtime to components, and then kind of transform that into a final resilience score. So first, I'll just give a high-level overview of the framework that we use for downtime calculation. And so this framework is basically applied to each infrastructure type and each hazard in our digital twin. So it starts by estimating the hazard intensity. So for seismic, we're primarily looking at ground shaking. For flood, we're looking at inundation depth. And for windstorms, we're looking at wind speed. And we're considering the hazard intensity at several different return periods for each of these different hazard types. So we get the hazard intensity at the location of a certain piece of infrastructure from a hazard map. And then that would be input into a damage model. And so Lisa asked about this earlier, and as I mentioned, for seismic buildings, our damage model, we have our own kind of developed in-house seismic machine learning model, which I'll show you a few more details about. And then for all other infrastructure and hazard types, we use fragility functions, which is kind of the traditional catastrophe modeling approach. Specifically for buildings, we do use vendor models for damage, but for other infrastructure types, there's actually not really that many damage models available. So we've developed our own damage models for like bridges, highways, all of the other types of infrastructure. We've either developed our own or used existing research and kind of brought it into this framework. So at a high level, fragility functions, there's an example shown on this slide in the damage model bin. Fragility functions are basically a set of functions that are given a hazard intensity. They predict the probability that your infrastructure or your building is in one of a few different damage states. So here it's shown, the probability that you're in a slight, moderate, extensive, or complete damage state, given that it experienced that level of hazard intensity. Then the next step in the framework is to apply a recovery model. So these are recovery curves, and they're developed for each piece of infrastructure, each hazard, and for each damage state. So this is basically kind of a probability for how long it takes that piece of infrastructure to recover or to get back to a state of being functional after it's been in one of the damage states predicted by the damage model. Again, there's not a lot of these recovery models kind of available, and this is something that more traditional catastrophe models don't really look at. And so we've done a lot of research here and kind of reviewed what's available and developed our own or adjusted kind of existing recovery curves from literature to fit into this framework. And then the next step is you basically take that recovery model, combine it with the outcome from the damage model to get a recovery curve for each piece of infrastructure in the digital twin. And then this is basically a curve that shows you, given time on the x-axis, what's the probability that your asset has recovered. And we basically interpret this recovery curve as a cumulative distribution function on the recovery time. So this is basically, you can get the time that it takes to recover and the probability that it's recovered at any time. And so then from that recovery curve, we can get to the final step of the framework, which is downtime statistics. You can basically just get the mean and the standard deviation of the downtime. And so that's kind of the overall framework. And then a lot of the work that our team at One Concern has done is kind of make sure that we have these components available for each infrastructure and each hazard type that we model. So bringing models from different places in literature or developing our own when they're not available and fitting them into this framework. And then this slide just shows kind of an overview of what I would call kind of our suite of damage and recovery model. So this is showing kind of like for every hazard and lifeline combination, what are the different metrics that we can model? So as we've seen, a few times before, the hazards are earthquake, flood, and windstorm for a few different climate scenarios, and multiple return periods. And then the lifelines that we include are commercial buildings. This is the first one on top. And for commercial buildings, we model the damage ratio. So this is basically a measure of the cost to repair the damage to the building. And this is kind of the typical output that you would get from a more traditional catastrophe model. And then for commercial buildings plus all of the other lifelines, which would be, power, transportation networks, and also what we call community, which is kind of a measure of damage to the residential buildings around a commercial building. We model the probability of damage and also the downtime to all of those different lifelines. So you can imagine we kind of have like a subcomponent impact and downtime model for each combination of hazard and lifeline shown on this slide.
And so question. The cost to repair a single building may be X, but if you had, a major disaster like a major direct hit by a hurricane or a big earthquake, then the ability to do the construction is quite limited. The costs are likely to be 2x, or at least bigger than X. Do you take that into account in the analysis?
Yeah, so the scale of the disaster, that's a really good point, especially like following a large scale hurricane, it can take a lot longer to get contractors to come in and repair. So I guess that's something that we want to do more research on and explicitly take into account to have some kind of scale factor to increase the time given kind of the size of the event. But so we don't explicitly account for it, but we do in the sense that our downtime models are based on a lot of historical downtime observations when it's available. So for example, like we've looked at historical hurricanes and earthquakes and kind of looked at the distribution of downtimes there. And so it's sort of implicitly accounted for that when you have kind of a large scale disaster, it will generally take longer than just if you're doing like a remodel of your home or something like that. Mm-hmm.
Thanks. Yep, that's helpful.
Mm-hmm. Yeah. Yep. And so now I'll do kind of a deep dive on one of the models that's in this kind of suite, which is our seismic machine learning model. So this is a model that predicts the probability of damage to buildings from earthquakes. So we apply it to commercial buildings and then also to what we call the community lifeline, which is a measure of the downtime to residential buildings. So this framework is showing kind of the traditional physics-based resilience model. And it's a series of steps that, maybe kind of looks a little bit similar to kind of the one concern downtime framework. But the main difference here is that it's really based on the application of fragility and vulnerability functions, which are based on kind of analytical approaches to understanding the damage to a structure. So what I mean by that is like the first step in this framework is looking at hazard analysis. So looking at, the probability that you will get some level of ground shaking at your building. And then the next step is a structural analysis where, these traditional models will look at building basically a kind of detailed computer model of a structure. And they'll kind of look at sort of a benchmark type structure. So a structure that represents, maybe like a concrete frame or a steel frame that you could use to cover a bunch of different buildings. And then they'll do a bunch of, structural analyses on this computer model to build a fragility function. So these are really based on kind of analytical models. And it's bringing in, a lot of engineering expertise and really kind of basing it on what's coming out of the analytical approach to modeling that structure to get the probability that it's damaged and then the recovery. So I think the thing that is kind of brought in that's unique about the one concern model is it's really combining a lot of this analytical expertise and these physics-based models with a machine learning model. So it's kind of bringing in both of those aspects because what's done in traditional catastrophe modeling is, there's a lot of expertise there and a lot of information goes into those analytical models, and it's very important to understand kind of that engineering foundation. And so what we do, we call kind of a hybrid physics-based approach, where we are using fragility functions, and we're using those essentially then as input to machine learning. So we're kind of taking all of the information that's contained in the analytical approach from a fragility function, and then essentially adjusting it based on what we've seen in historical events. So the input features to our machine learning model are shown here. The input features are actually kind of the outcome of a fragility function. And the fragility function is based on characteristics of the building itself. So based on the building material, the structural system, the construction year, and the building height. And so that is a set of inputs to our model. And then other input features are things like VS30, which is the soil condition. So that tells you how soft or stiff the soil is underneath the building, which can have a big impact on the shaking level. And then also multiple intensity measures for the earthquake. So we can look at peak ground acceleration, peak ground velocity, spectral acceleration at multiple periods. And so this is also something that I think is interesting and unique about the machine learning model, because traditional fragility functions typically take one intensity measure as input on the x-axis. Like they'll look at either PGA or spectral acceleration at one period. But using a machine learning approach, it's a little bit easier for us to account for multiple shaking intensities. So we use all of those as input to a machine learning model that's trained on historical damage data. And then the outcome of that model is the probability that our building is in one of several damaged states. So it's an outcome that is basically consistent with what you would get from a fragility function. So you can use it sort of in the same framework. So this slide just shows kind of a snapshot of the historical damage data and the data that we use to train our machine learning model. So one of the challenges in this space, right, is getting access to damage data because thankfully earthquakes are pretty rare, and then damage from earthquakes, especially in the US, is even rarer. But we've been able to collect a data set through a few different sources. Some data is publicly available, like from the 2014 Napa earthquake. Some damage data sets we've gotten through partnerships with local governments, like from the city of Seattle or from Cal OES for the 1994 Northridge earthquake. And then for some earthquakes, we've actually sent people from our company out into the field to collect damage data. Like we sent some people to Anchorage, Alaska in 2018 to collect damage data. We sent some people to LA to collect information from the Ridgecrest earthquake. And then we also use synthetic data sets to train the machine learning model. And these are basically data sets that are created by OneConcern using fragility functions. And we use these to kind of fill in the gaps in the observed data. And so that's another way that I think our machine learning model is really a hybrid model, because it's essentially combining the outcome from a physics-based fragility function. And then it's kind of, I think of it as almost like tuning those fragility functions based on what we've seen in the historical damage data to kind of get kind of a more fine-tuned prediction on the probability of damage to a building. And then on the left here, I'm showing a bar chart just to kind of give you a sense of what the output looks like from the different data sources. So this is showing the expected number of buildings in each damage state from a few different models. In orange is the observed data, so the ground truth data. And then in blue is the output from our machine learning model. And you can see that it matches the observed data fairly well. And then in green is the prediction from a fragility function. And this is the fragility function that we're using in our hybrid model approach. So you can basically see how the green bars are a little bit off from the observed data, and then the machine learning model kind of tunes it to bring it closer to what we've observed in historical events. All right, and so now I'll talk a little bit about the resilience score. So this is sort of how we bring all of that data together. So first, I'll flash up an equation for the resilience score. So this is meant to be sort of a high-level description that just kind of contains all of the different components that we include in the resilience score. So first, 1CRX in the second equation shown here is our acronym for the OneConcern resilience score. And you can see that we set it equal to kind of the mean downtime for this building plus some number of standard deviations, plus 2 standard deviations in order to take into account the tail risk. And then the equation above is how we calculate the mean downtime for a given building. And I'll kind of walk you through the different components of that equation. The different pieces are, the first one is DS, which is the downtime statistic. This is a random variable, and it's a random variable that represents the downtime at that building. And so this is essentially the recovery curve that comes out of that downtime framework that I showed a few slides ago. So we have a recovery curve for the building, which is basically a CDF, or a random variable. And then F of that DS is the probability density function. So basically what we're doing is we're integrating over the probability of that downtime times the downtime. So that gives us an expected downtime given an event. So that's what this kind of first integral is doing. And then the second integral is integrating over this variable that we call lambda. And lambda is the annual rate of exceedance from the hazard map. So it's equal to 1 over the return period. Basically, what that means is we're integrating over all of the events that can happen at this site. So we're getting the expected downtime for all of the possible events. So we're adjusting for kind of the frequency at which those events occur. And then the third integral is over a variable called T, which is the planning horizon. So this enables us to look at kind of multiple time horizons into the future. So an insurance company might be interested in like a 1-year time horizon, because that's how long, they will be holding an insurance policy before it needs to be renewed. Versus like a financial institution might be interested in a 30-year time horizon, because that's the length of a mortgage that they're giving on a commercial building. So they might be interested in understanding what's the downtime over 30 years. And so basically we can integrate over that time horizon for all of the possible events that might happen and all of the possible downtimes that would occur. So the one concern resilience score is really sort of a probability adjusted mean downtime that can happen over some projected amount of time into the future. And it's coming from downtime to the building and then all of the lifelines around that building that we've kind of been discussing so far. And then I'll kind of walk you through an example of what this calculation looks like from one building, looking at kind of all of the different data sets that are included. So this is just kind of a contextual example to give you kind of a sense of the scale of all of the data that goes into calculating the resilience score for one commercial property. So what's being shown here is, let's say we have this building B, and that's the commercial property that we want to calculate the resilience score for. And building B is in the center of each of these maps here, and it's a location in southern Florida near Miami. So basically what we do is we look at that building in the middle and we calculate the downtime using our impact and recovery models for all of the surrounding lifelines. And this is for one given peril. So for example, for wind, and one given return period, for example, like 100 years. And so then basically what we have here right on the far left is the community. So what we're looking at, all of those little dots are residential buildings around the commercial building. And we calculate the downtime to each of those, and it's probably tens of thousands of residential buildings all around that commercial building. We also, have generated in the middle map, we're showing building B again in the middle, and then the power network around it. So you can see our synthetically generated distribution network where we have the substations shown in yellow, and then the power lines connecting that building to the possible substations. And we basically, run that simulation and calculate the power downtime to building B using this full distribution network. And then we also consider transportation, which is shown in the map on the right. So we have, again, building B in the middle, and then kind of all of the yellow cloud around building B is the road network, and also all of the bridges around building B, because there's actually many bridges, because we're considering all of the highway bridges, so highway overpasses and that sort of thing all around building B. And so that's showing the downtime for basically probably, a few hundred bridges and 100 roadway segments. And then we're also looking at airports and ports, which are shown. You can kind of see the red anchor on the coast. That would be the downtime to a port. And then farther north, we would be predicting the downtime to the airport and the port. So we basically start by calculating the downtime to all of these components for one peril and one return period. And then the next step is we basically repeat the same analysis for all of the perils that we include, all of the return periods. And so for seismic, it's 10 return periods, and for wind, it's 15 return periods to kind of cover the whole kind of space of possible intensities of these hazards. And then we also calculate that for all the different climate change scenarios. So this slide is just kind of showing, like, for example, for seismic, you can imagine we kind of have that map repeated over and over again for each return period. For windstorm in the current year of 2020, I know it's 2023, but we use 2020 as the anchor year. We calculate that map basically again for all of the return periods. We do it again for wind in the year 2050, considering RCP 8.5. We do it for flood, and so we do it for all of these kind of permutations of possible climate scenarios and hazards. And we have basically this map showing the downtime to all of the different lifelines around a building. So as you can imagine, it's a lot of data points that all go into the resilience score for just this one building. And then basically we need to combine all of that information into one final metric. So step 3, we basically start by, you kind of saw on this previous slide, we kind of have like a stack of different maps that represent different return periods. We integrate over those return periods. And that was sort of the middle integral from the first slide, or from the equation that we showed. So we integrate over those return periods, and now we have kind of an average annual downtime given a peril. So for seismic, wind, and flood, and for a given lifeline for that building. Then the next step is we need to integrate over the lifelines. So, for like earthquake or wind, we consider all of the lifelines and we choose the maximum across in order to get kind of one representative downtime for that peril. And then finally, we integrate over the perils. We sum across the perils. We consider the downtime to be cumulative in order to get kind of the final integrated downtime that we then use for the resilience score. So you can kind of see how we've generated a bunch of data, and we're considering downtimes across kind of all of these different events and all of these different lifelines, and kind of distilled it down into one final score that you can use to give kind of a snapshot of the resilience of a building. And so this would maybe be the final metric that someone might use to like rank or compare two different properties. But then if someone is interested in understanding all of the details that went into the score, you'd be able to go back and get all of the individual components that you could then use to really understand what's driving that resilience score and help make decisions about maybe where you would want to do some mitigations in order to help improve your final resilience score.
Lynne, did you mention that and I missed it? What is the weighting scheme for each of the components of the downtime? Like, are you weighting the power going down more or less than transportation? Like, how do you combine these components?
Yeah, that's a great question. So it's not explicitly put on the slide, but so when we integrate over the lifelines for each peril, we're taking the maximum across the different lifelines. And so, if you consider a building and it has power downtime and a, downtime from the highway, we kind of consider the time that that business is down as sort of the maximum across all of them. And so the assumption in that is basically that the property is kind of back to its original level of functioning once all of the lifelines around it are back to its original level of functioning. And so we're taking kind of the worst case.
Yeah, it's the worst case, like, and you don't discount it, like it's not like a 95% VAR, it's like 100% VAR.
We're taking the maximum downtime across all of them. Okay. Yeah. And the reasoning for that is, I think, to kind of take that worst case approach. But this is something where, if you as a company are interested in understanding your resilience score, or you might have like a different use case for it, right? Like there's lots of different use cases for all of these analytics. And so some clients might be interested in adjusting how we do that integration. And we've definitely had conversations with people who are interested in maybe changing it. For example, insurance is an interesting use case where they might want to consider, like maybe they don't care as much about the residential buildings, and so they just want to drop that. Or they might not care, there might be a business that doesn't really depend on airports, and so they might want to drop that from the integration. And so that's something that you can kind of go back in and adjust and do in order to kind of adjust your final resilience score. So a lot of these metrics, we kind of define like a default view on it, but we can definitely work with anyone to sort of adjust these assumptions if they have better information about, what's important for their business.
Yeah, nice. Thank you. And there's like a question for you in the chat.
Okay. Let me pull it up.
Can you see it? I'll read it. Thank you, Zach. Beyond the scoring, do you calculate event-based downtime as well? For example, given an actual hurricane and known inundation damage, what's expected downtime for that given event?
Yes, we do. So this kind of overall framework can work really given kind of any hazard input. So if you wanted to, understand what's the downtime for, an actual hurricane that happened, you would just need to know like what was the maximum wind speed at all of the locations in that hurricane, and then you can run our model to get the downtime. And we've done that in order to do validations on all of these models. So we've run it for, some historical earthquakes like the 1994 Northridge earthquake, and also some more recent hurricanes in Florida. We just recently did a validation for Hurricane Idalia, which happened earlier this year. We've looked at Hurricane Ian and Irma. And so that's a way that we do validation on the models. So, yeah. Thanks for the question. Mm-hmm. Yeah, and if you're curious, I think we do have some blog posts on our company website about some of those validations. I know that we're working on one on Idalia right now that will be released soon. So you can kind of see how our predicted downtimes compare to what actually happened in that event.
Great, thanks. I'll look for those.
Okay, and so here is kind of a summary of, using this kind of default methodology that I described to calculate the 1CRX across our entire digital twin. So this is for, as I mentioned, we basically pre-calculated 1CRX for all of the 39 million commercial buildings that we have in our database in the United States. And then this is showing the median 1CRX for each county. And one detail on kind of the final 1CRX, right? It's based on the downtime, but then we basically discretize it into 20 grades at the end. And so the final resilience score is a grade between 0 and 20, where 0 is the worst resilience. So it's the lowest, which means the highest downtime. And then 20 is the best resilience. And so as you can see on this map, right, it pretty much lines up with, I think, what we would expect to see from this kind of score, where you have basically the lowest resilience along kind of the, South Atlantic, the Southeast United States, where we have very high hurricane risk. And that area is, very impacted by both wind and flood. So you would expect to have very high downtimes and very low resilience in that area. And also we have kind of low resilience scores on the West Coast, where earthquake hazard would be high. And so that would lead to kind of lower resilience. And then maybe in the middle of the country, we have kind of higher resilience scores because those areas would be less impacted by natural disasters. But you do see some interesting areas kind of showing up, where you might have little pockets of higher flooding hazards, or, like the New Madrid seismic zone kind of in the middle of the country, where you might have some lower resilience because of some unexpected maybe seismic hazard. And then this slide is just showing a little bit more detail about the 1CRX as we've kind of calculated it. So this is showing a empirical CDF for all of the 39 million buildings in the US, broken down by different census regions. So basically what we're looking at here is on the x-axis, we have the resilience score, again, where the far left side is a score of 0, which is low resilience. And on the right is a score of 20, which is high resilience. And then on the y-axis, it's the probability, that there's kind of the proportion of buildings within each census region that has a resilience score of that or higher. So you can kind of see, like if we look at, for example, the Pacific region is the brown line, which is kind of the highest line here. And what that means is if you look at, the 50% y-axis, that means the median resilience score in that region is 10. So it has basically the highest resilience score out of all of the census regions. So it's kind of the worst case. So it has the lowest resilience on the West Coast, the lowest median resilience. But what's also kind of interesting is you can look at other regions, like, for example, the South Atlantic region in pink. This is the southeastern portion of the United States where hurricane risk is very high. And so what you can see is even though the median resilience score there is higher, showing better resilience in the Southeast than, the West Coast, you can see that the variation is a lot broader. And what that means is, if you look at sort of the lower tail, maybe at low resilience scores of 6 or lower, there's actually a much higher percentage of buildings in that region that have a much lower resilience score than you see on the West Coast. And so what that's telling you is within the South Atlantic region, there's kind of a high percentage of buildings with very low resilience, but then there's also more buildings that have higher resilience. That's kind of making a much broader, more variable distribution. And again, I think that kind of matches with our expectation because you can imagine buildings maybe right on the coast. There's a fewer number of those buildings, but they would be much more impacted by flood and wind from hurricanes. And then I just want to highlight kind of one interesting case study for 1CRX. And this is kind of speaking to potential use cases and how, we kind of have this one final aggregated metric at the end. But then what you can do is really go back and like really break it down into the individual components to give you some kind of unique insights about different properties. So for example, in this case study, we're comparing two properties, property A and B in Florida. They're very close to each other. They're only 0.7 miles apart. If you used a traditional catastrophe model, you would find that the damage ratio for both of these properties is about 1% over 10 years due to a wind hazard. So from that perspective, they look very similar to each other. And if you're, trying to make a decision about which property to invest in, using, those first two bullet points, you might think, oh, well, they're very similar investments. One is not really any more risky than the other. But one thing that's interesting about 1CRX is if you looked at it for these two properties, you would see that it's very different. And if you dig into why, you would see that property B has a very high power downtime of 8.5 days, while property A has a downtime of 0 days. And the reason for that is because property A is right next to the power substation. So the probability that the lines are damaged in a windstorm is very low. So the power downtime, it's basically very low because there's not a high chance that the lines are going to get damaged. Whereas property B is much farther away from that substation. So the probability that the lines get damaged is much higher, leading to a much longer average downtime. And so that's something that, you can use the 1CRX metric to kind of learn more information about the difference between these two properties. And so with that, I just have some kind of closing bullet points. Just kind of a summary of what we've talked about today. Right, One Concern has kind of developed this resilience platform at scale. So we've, built the large digital twin over the whole US, keeping scalability in mind in order to, build this digital twin and then be able to run all of the impact and recovery models across it. So this kind of approach really enables high resolution resilience analytics, right? We can get this 1CRX at the building level. So we're really calculating it at the individual property level, which is something pretty unique. And then this resilience score enables you to compare kind of across buildings, geographies, and time, which really helps you do risk selection, I think, in a way that some other metrics might not be able to. So it can really help you kind of uncover some unique insights. And so with that, thank you very much for your attention and all of the interesting discussion. And I'm happy to take any other questions that you guys might have.
Thank you, Lynn, for a beautiful talk. We do have 6 minutes. So are there any further questions from the audience?
I have a couple, but I'll wait for someone else who wants to speak since I took some time already.
Well, let me just make one comment. We're looking at also extending this to adjust pricing on risky debt. So that's another extension that is under research. I just mentioned that in case other people are interested. It's really about adjusting those default probabilities for physical risk.
Yeah. An old subject of ours, Jeff. Look forward to that.
Yes.
Well, I think that would be extremely useful adjustment. I have a couple questions to Lynn. So my previous question about the weights, right? So let's say the building, you evaluated the resiliency of the building, and the building put solar panels on. How much would that affect the score of the building if that happened? Like, what's the impact of that?
Yeah, that's a great question. And that's something that you can adjust for because you can basically reduce the power downtime by adding in solar panels. And so I think, you know, the impact on the final resilience score would depend on kind of the specific details of the building itself. And so, you know, if power downtime is the main driver of a bad resilience score and you install solar panels, then it, you know, would basically decrease the downtime that would then, you know, increase your resilience score. And that's something that we've thought about. And I think we've even talked to some solar panel companies and some startups that are interested in that, thinking about how you could do sort of like a ROI type calculation, you know, like the cost of installing solar panels and being able to help justify the cost of that by showing how much it would decrease your downtime, which, you know, would lead to, if you decrease your downtime, you know, don't lose all of that revenue. So that's definitely something interesting that you could do with this.
Right. And I also wonder if you know the answer to this question, will Millennium Building in San Francisco fall over if we have an earthquake?
That's a good question. Something that Jeff and I have talked about many times. Yeah, I mean, I can't say with certainty if it will fall over, but there's definitely a lot of issues around that building with the foundation and not considering, you know, the specifics of the soil underneath. And there's a lot of concern there. So, you know, that's something where, you know, you really have to take into account the high resolution information. And yeah, I would say it doesn't look very good. Yeah.
Oh, if you find out what the actual score is, could you please email it to me?
Yes, we can look up the score for that building. Yeah.
Thank you for the great talk.
Yeah, thank you. Thanks for all of your questions. It's a great discussion.
Really great talk. And as I said, we love to see you in person on campus when you can make it.
Yeah, I definitely hope I can make it soon. Yeah, that would be great.
Terrific. So some announcements. We will not be meeting next week or the week after for Thanksgiving break. And then our final talk, which is the Thursday which is the Tuesday after Thanksgiving, is going to be by Chaim Bar of University of Connecticut. There's not a post yet of his title and abstract, but I actually know what it is. It is on high dimensional algorithms and high dimensions. Maybe some of them will be useful to you guys at One Concern. Basically exploiting the difference, exploiting what we call the blessings of dimensionality. Miracles that happen when you have a lot of predictors and not very many observations. So please do join us. This will be on Zoom. Chaim's not going to be able to make it out this time, and hope to see many of you then. Wish everyone a wonderful Thanksgiving and have a great rest of day. Bye now.
All right. Thank you. Bye.